can start this thematic symposium on fracture and fatigue in presence of cracks or stress concentrators. It's organized by the Technical Committee number 3 and chaired by me and my co-worker Andrea Zanichelli. I would like to thank all the speakers that have made possible the realization of this symposium, organized in 7 sessions, and thank you to these great results. Therefore, we can start with the section 1A. I would like to remember you that each speaker has a maximum time of 12 minutes for the work presentation. Okay, the first lecture is entitled Experimental and Analytical Investigation of Low Cycle Fatigue Damage at Notches in a polycrystalline nickel-based alloy, and is presented by Bernard Fedelich. Okay? You can use this, and this is the pointer.
Okay. Okay, does it work? Okay, thank you. So I'm going to report on the work that has been done as a collaboration with Siemens Energy, and the work has been done by our PhD student, Adam Butz. So it's about cooling holes in turbine blades. These cooling holes are used to generate film air to protect the metal from the hot gases. Unfortunately, these holes are also the source of cracks because the material is severely damaged by laser drilling, and we need to be able to predict the evolution of damage at these holes. There are several challenges with this. One challenge is the fact that we have stress gradient at the notch. We have also a size effect, and the material, it's a polycrystalline nickel-based superalloys. It has a very coarse grain structure with grains a couple of millimeters. So at first we have performed tests with specimens that contain holes. We see the specimen on the right side. These are cylindrical specimens with a rectangular central part, and the central part there is a single hole. The tests are strain control, and the fatigue life is defined by a given load drop, here 5%. So you see on the right side the test apparatus. You see the specimen in the, whoops, it was a bit too fast. The specimen in the middle with a hole here. You see the induction coil. You see the extensometer. So in some cases we also use a thermographic camera to follow the cracks, and you see also here the potential probes. See an example of the results here. You see 2 cracks that emanates from the hole. This is about the end of the test. You see when the specimen is broke that you have 2 cracks on each side of the hole, and if we measure the crack length, we see that the crack starts to grow quite immediately and then reach some critical size. So the first important task was to try to characterize the size of the defects before the test. You see here one hole, and you see that we have already some cracks perpendicular to the hole before mechanical testing. So we have prepared a plate containing a number of holes, and we made a number of cuts in this plate to examine all in all 48 sections, and we found 72 defects, crack-like defects, and we performed some statistical analysis of these defects. Here you see, for example, the number of defects in at one hole, and we have also here, whoops, the probability distribution for the size of the defects, which are assumed to be circular cracks. Then we have applied a fracture mechanic-based lifetime model, which is inspired by the EBS model, which was developed by our colleagues at BAM, Uwe Zerbs and Mauro Madia. So since it's a fracture mechanics-based model, we need some equation for crack growth. It's based on the modified Nazgul equation. You recognize here on the, it's quite sensitive, this thing. On the left side, a term which describes Paris regime. It includes the plastic corrected stress sensitive factor of the range of it, which depends on the delta J. It includes a factor which corrects for crack closure. Here it depends not only on the load ratio, but also on the crack extension. And here on the right side, you see a term that describes the impact of the threshold. And the threshold is assumed to depend on the crack extension also. So we have performed a number of crack propagation tests here. I apologize for the fact that the axes are scaled for confidentiality reason. So we need to characterize or to describe the evolution of the threshold. The threshold actually increases from its value at the beginning, which is the intrinsic effective threshold, and due to plasticity-induced crack closure and oxidation and also roughness, it increases up to its value for a long crack. So you have two solutions. Either you perform some tests, special crack growth threshold tests for short cracks, which are quite expensive. In this case, we have used an analytic model, which is this analytic model, which says that the threshold it increases from its initial value to the long crack threshold, and it includes a fictitious crack length after El-Haddad, which is connected itself to the fatigue limit, delta sigma threshold, and to the long crack threshold. For the intrinsic threshold, we have taken a value from the theoretical value from literature, and the crack closure factor also varies between 1 and decreases down to its value for long cracks. So first we applied this model to smooth specimen as a kind of validation. For this we have used the Rambert-Osgood model to characterize the cyclic behavior of the material. We have calculated delta J with results from the literature. The value for the long crack threshold has been extrapolated from our crack growth test. We got some value from our partner Siemens for the fatigue strength limit for smooth specimen, and as an initial crack size, we took 10 micrometer, which is about the size of the carbides. So here we have compared predicted and measured fatigue life for two diameters of a specimen. We have quite a good agreement. Next step, we have applied this model to our specimens with a hole. So first we need some assumption for the crack shape. And we consider two extreme cases. The first extreme case corresponds to the case of a through crack, so through the hole thickness. So in the middle you have the hole here. And the second extreme corresponds to the case of a half circular crack. We have calculated delta J by finite element. As the size of the initial defects, we have taken the median for the distribution of the maximal size of defects at a particular hole. Then we applied the model for these two extremes, and we see that the experimental points, these black points here, lie quite well between these two limit cases. So to improve our estimate, we made another assumption, the following assumption, that at the beginning we have initially half crack that start growing independently from each other, And when they touch, they merge and form the through crack that then continue to grow. For the initial crack size, now we take the average crack size that we have determined as, and that's the initial distance we took the inverse of linear crack density. And here we see, at least for the large loads, we have a quite good agreement. For the small load, we underestimate the fatigue life, and it's probably due to the rough estimate that we have done for the threshold, for the long crack threshold. So now to conclude, we have seen that the fatigue life of the specimen with cooling holes is governed by the crack propagation phase. The fracture mechanics base model that we have used need a lot of data about, especially about crack growth threshold, which is quite critical point, but also initial crack size, and we need some crack growth measurement. And we have still some large uncertainty, in particular regarding the threshold, and this is also due to the fact that we have a coarse microstructure which we could not take really into account here. Actually, we assume implicitly that we have microstructural large crack, which is of course not true here. So as a last slide, to acknowledge our funding from our partner Siemens and from the German government, and to thank you for your attention.
Thank you for your talk. Any question or comments, please?
Okay, I'm not sure if I understood well. It was a low cycle fatigue study, and there was a lot of talking about threshold, which has very small cyclic plastic deformation. Can you make a comment on it?
As you have seen, the threshold actually increases from its initial value for short crack to its value for a long crack. So it seems that for the large loads, the threshold has probably not such a big impact. But for the small loads, it seems plausible that the threshold, particularly the long crack threshold, so its maximal value could have some large impact.
I would like to ask you 3 quick questions. What is the typical diameter of the holes?
0.3 millimeters.
And how dense are they? The distance between every 2 holes?
You mean in a blade?
Yes.
It's a couple of millimeters. But,
a couple of millimeters.
Yes.
So there is a way to avoid the cracking. Just a hint. I can talk with you later, but there is a method called cold work, or in other words, autofrettage. If you enlarge a little bit the holes plastically, you will have no cracks.
Okay. And to forward this recommendation to Siemens.
Well, it depends how much they pay.
Thanks for the talk. You've talked about evaluating delta J from FEA quite a lot. So when you're doing that, do you evaluate a monotonic J for a specific load, or do you, and then equate that to a K value and that's your delta K, or do you evaluate a cyclic delta J through, with cyclic material properties through the loading, and then take the top and the bottom of the cycle as your delta J, and then convert that to a delta K value? Does that make sense?
Yes, we evaluated the delta J based on cyclic properties which were modeled by the Rehmer-Osgood model.
Thank you for a nice presentation. I have a very simple question. Have you measured the crack length increment during this cyclic test?
In the cases in which we did it by the potential drop method and also by thermography camera. But the best actually is the potential drop method. But, well, we have seen crack propagates on each side of the hole, more or less symmetric, of course, not perfectly symmetric, and the potential drop method gives you only an integral measurement.
Thanks for your interesting talk. I had a more experimental question. You were talking about crack opening and closure, and also your use of, I guess, DCPD for crack length measurement. But in the beginning, you showed that there were multiple cracks within the range. I'm guessing you're using the extensometer to control your fatigue experiment. So would 2 or more cracks not actually affect your crack length measurement with DCPD depending on your electrode setup? And also, how do you account for if the cracks are completely open? Do you place more displacement on it, or you know, when you're measuring? How do you account for the multiple cracks within extensometer range?
I'm not sure whether I got really your question. As I mentioned, the potential drop method is an integral measurement. So it will not allow you to distinguish between several cracks. Now, for the model, for the last version of the model, we assume that several cracks start to grow from the beginning, because we have seen that in a single notch, in a single hole, you have a number of initial defects. I don't remember the maybe 10 the order of magnitude number of defects. And we assume that they all start to grow in parallel. Of course, it's very simplified, but it's plausible, I would say.
We have finished the time. We can continue later, okay? Thank you again.
Thank you.